The functional safety workflow of internal IP NPU within a large automotive-wide through analysis and emulation usage for software-based safety mechanisms. The abstract. As the number of semiconductors used in the modern cars dramatically increases, safety is become the dominating factor in the automotive semiconductor's lifetime. Achieving the desired safety level is burdened by the runtime of the fault injection and data management over the duration of the fault campaign. In this paper, we describe the process of data management and fault injection runtime optimization that reduce the time to achieve the desired safety level and the product certification. This paper gives a case study of the fault campaign flow for internal IP NPU in a large automotive device by using the emulator for software-based safety mechanism. Introductions. According to the ISO 26262, standard functional safety is the absence of the unreasonable risk due to the hazard caused by malfunction behavior of the electronic systems. Safety managers handle hazard analysis and risk assessment HARA at the stage of each hazard event, HE assigned to within the automotive safety integrity level, ASIL, and based on the safety and severity of the classification, such as the potential harm, S, probability of the functional operational situation, E, controllability by the driver or the other traffic participant, C. Then the each AE. The safety manner defines the safety goals and sets the functional safety requirement needed to fulfill those safety goals. During the protocols developed, the functional safety requirement comes down to the technical safety requirement and further to the hardware HW safety requirement and above the software safety requirement. Both based on the assumption of the use of certain IP inside the automotive SoC, which contribute to the certain safety goal is assigned with it needed safety requirement. The safety mechanisms SM are integrated into IP and are intended to verify the associated safety requirements. To prove the effectiveness of the SM, diagnostic coverage DC is measured. The DC expressed the capability of SM to discover the fault and is calculated by dividing the number of the failure detected by the SM by the total numbers of failure in the electronic systems. ASIL determined by single point fault metric. SPFM is the level of the coverage provided by the SM for a single fault and the residual fault. For example, to satisfy the ASIL B and the SPFM greater than or equal to the 90% is required. Table 1. Table 1 is SPFM is the value for each ASIL. After the SM information within the expected DC and expected protection area is defined for the campaign process continue to the identification of the alarm net and observed net. The next step is determine the generated tested scenarios followed by the fault injection. Workflow the fault injection at 3 steps. 1. Generate the fault list and injection the fault list and the reported matrix. Siemens provide a smooth flow for the above the steps and a single function safety database. FUSA DB is used throughout. Chapter 2, the NPU safety verification with the safety mechanisms. The NPU IP figure 1 is part of the automotive SoC and contributes to the safe video sensing. NPU provided the fast and energy efficiency hardware acceleration for AI and ML application in computer vision, imaging process, and other domains where the state-of-the-art deep learning network are used. NPU consists of several processing blocks, PU, P1, and P2, PU2, and a memory access block, MEM, and control block is controller. It's a CTRL. A safety island is designed to manage and monitoring all of the safety content within the automotive SoC, in particular fault management unit, FMU, in the safety island collects fault and reports related safety event information. The list of SM table 2 is defined by the safety manager as the state of the request of fault verification. The typical memory plans are protected by the penalty and UCC at the SM9 and the SM13. Related fault signals are connected to the FMU directly, and while large parts often require software-based SM like self-test, SM2 and SM3, where the firmware is needed to control the intended function. So the firmware checks the behavior and certain fault signals. Majorly FC and SM protecting the memory parts of done as using a simulation flow. This paper deals with FC for a software SMs, which was conducted using an emulation flow. The goal was to verify the DC defined in the level of the 90% ASIL B and considering the margin of the error of the 1.21%, the expected DC should be greater than or equal to just 91.21%. Failures in time, feed rate metric, proportion of the number of the transistors in the die was used based on a FIT-rated attribution for logic and memory parts of each block inside the NPU. Then expected DC for each block was estimated. So that it was decided to use SM, SM3, SM1, SM2, Table 4, mandatory SMs and other SMs as additionally as the contribution of the overall DC score is insignificant. For SM3, security mechanism is which protected all blocks the expected DC was set to 91.21%, and for SM1 and 2, which protect our CPU inside the CTRL, the controller block, the expected DC to set to 60% was sufficient. The final DC for an NPU can be calculated by the weighted average of the DCs for all logic and the memory parts. Figure 1 is a block diagram of NPU with related SMs. Table 1 is the SMS targeted for emulation and simulation. Table 3 is expected DC for SM3 self-test. Table 4 is expected for DC for SM and SM2 and CPU. Chapter 3 is the simulation methodology. To facilitate the FC for the complex SW-related SMs to make this verification feasible within the achievable time, hardware system verification tools like an emulator are required. Since emulation was one of the options to be used for the functional verification of NPU, it is easy to add additional scenarios for the target DC and use this emulation verification environment. If the target design is big and the scenarios needs to be long, emulation FC is the best option in terms of runtime to set up the environment of FC, the fault list generation, the fault injection run, and the database for fault list and the results are required. As a few separated steps for FC are required, Siemens closed loop toolchain is chosen for NPU FC. The fault listed by the safety scope, the RTL, and the fault decisions net FDN are input to a compile DB, and the generated fault list is stored into a FUSA DB compilation by Veloce. Refer to the FUSA DB for the fault list and the 5-volt FDN. FDNs are those nets whose values are stored during the golden run and compiled during a check run. And there are two types of the FDN: the alarm or observed net. The alarm net is a signal and can reorganize when there is a safety violation. The observed net is a net signal that a Veloce can recognize. Then there is a safety violation. Veloce fault app is used to inject fault on the fault list. Finally, the result of the fault injection run is stored into the FUSA DB, and workflow is represented in Figure 2. Figure 2 is a fault campaign using an emulation flow. The output of the compilation are the fault injection and net, FIN, and the blocks as necessary for Veloce emulator. FIN, which is an output of compilation, will be doubled of fault net in the FUSA DB because the Veloce assigner stuck at 0, SA0, and stuck at 1, SA1, and the fault net. Only permanent faults are considered SA0 and SA1. Other fault types like transient fault and etc. are also supported by the beyond the scope of this FFC. The FUSA DB has the end of the fault net, the output of the fault list from the compiled DB, will be to end and SA0 and SA1 for each fault net. Some fault can be optimized out of this stage. There are several types of non-required fault injection run. Veloce provides optimized method to increase the running performance by skipping a fault injection run. That logic, and fan out of the FIN does not have any reader, and means that fault impact cannot be propagated further. This logic can be optimized as that logic. no port in memory. In the design, there is a memory that addresses anywhere. There will be no way to the design is affected by injecting fault. Memory, which is not read anywhere, will be optimized as memory. No read port in memory, fin and FDN. If a port net is defined fin as FDN both by user, this fault net will be optimized as fin and FDN fault. IDs are assigned to each fin after compilation, net including the optimization net. This ID-based fin provided for each fault injection run and environment setup. The FDNs are captured during the execution of the last test scenarios on the emulator, and the result are served as a reference values golden run. Golden run means the normal will run without a fault impact, so that the run will be record or behavior of the FDNs to be referenced. That each fault from the FIN is injected during the execution of the same test scenario, and FDNs follow check run against the reference. Figure 3. As a result of the check run, the alarm cannot detect it or undetect it. The fault can be observed or unobserved, thus to give 4 cases: D0, DU, DUO, and UU. Check run means run with a fault impact can be observed or detected by comparing them against the golden run. As the number of the fault to be injected can be used, check runs are detected in the emulator in parallel. Add vector analysis fault nodes are checked, and those with the constant values are optimized off or from the injected list for this tested scenarios. To save runtime more, it can be achieved fast fault injection runtime by excluding unnecessary time, such as system initialization time. The initial state of the DUT before a trigger signals can be used for a golden run and the source for each check run. The figure 3 is the golden run and check run. During the fault injection run, additional runtime is necessary after the alarm detected and the observed net is observed. By applying the early termination feature, fast run can be also achieved based on the number of the DO cases. Finally, the results emerged for test scenarios from the given SM. They are classified and used for the calculations of the ASIL and FDMA the matrix. If score is not enough for the test scenarios are regenerated and FC is restarted. The generated of the test scenarios are for FC. The typical test scenarios FC includes the following steps: host boost CPU, CPU 1, host CPU, host boot CPU, 2, CPU activate the watch the timer WDT, and 3, CPU triggers command scheduler CMNS to start the operation. 4. CMNS configuration internal block. 5 is the CMNS control the internal blocks which repeat, read input and process data and write output. 6. The CMNS wait internal blocks and end. 7 is the CPU gets interrupted from the CMNS about the operation end. 8. CPU triggers the MEM operation to generate the CRC and or releases the CRC generated by the internal blocks at step 5. 9. CPU compares the CRC with the reference. 10. If the comparison failed, the CPU sends interrupt to alarm fail. Otherwise, steps 3 to 9 can be repeated. 11. If all operations end, CPU sends interrupt alarm underscore pass. 12. CPU stops WDD. If the WDD triggers before the CPU sends pass or fail interrupt, the CPU sends interrupt alarm hang. If it also is that a CPU makes a CRC comparison once after all operations end. Test scenarios for FC must meet 2 conditions, both high quality and short runtime. High quality means that if test scenario does not satisfy the above metric, then it should be generated. To get a DC greater than or equal to 90% required to ASIL B, one should make the test scenarios with quality above the sign-off level, and the test scenarios used for functional verification. On the other hand, the test scenarios used for function verification often cover each function with redundancy, so it takes a long time to run all test scenarios. However, the test scenarios for FC should also be used for error detection in the actual field test, and those scenarios should be completed in shorter time because they should not affect by the actual software operation. There is no simple method to make the ideal test scenarios, but there is an accurate and the confidence but slow method through the analyzing the IP specifications algorithms, adding the features one by one. The following points can be considered to generate high quality and test scenarios more efficiently. One, test scenarios in the real software does not have a DC as high as expected. In general, software safety function scenarios do not utilize the all IP functions. Depending on the scenarios required by the system, IP functionality may be active or inactive. If the certain functions of IP continue to be inactive, those functions can be excluded from the DC measurement range. However, software engineers generally do not guarantee that certain IP features will continue to be inactive. This is because the function can be activated again depending on the scenarios. So one should provide a test scenario that satisfies a higher DC compared to the test scenario used in software. In general, to obtain the digital DC achieved the ASIL B, it is needed to utilize the minor functions in addition to the main function of the IP. So the test scenarios used in the functional verification can have a higher DC. As the starting point, it is advisable to measure DC for a test scenario used in functional verification. In a lucky case, it is possible to achieve ASIL B with only those scenarios. However, this case is rare. If you achieve the ASIL B with the test scenarios to get a shorter time, it is possible to rank the test scenarios by total coverage to remove the duplicated test scenarios. It's good if the contributing the test scenario satisfy the DC and execution time, otherwise its optimization is required. 3. If a test scenario for FC is newly generated, you should be able to detect both the system hang and data mismatches by fault. In particular, if the system IP has a chain of the multiple sub-IPs and a fault is injected into sub-IP in the form of the part of the chain, and the failure is not propagated and it usually cannot be changed by the configuring by the sub-IP in the back of the chain. To solve these issues, one should configure the issue sub-IP data can react sensitively to small fluctuation caused by the fault. 4. As the change by the Wonil speed requires intermediate values like 8000 hexadecimal 7FFF are more advantageous than the extreme values like H0 and H4Fs. The fault is injected into register or port by 1 bit, so the test scenario should be able to detect the fault caused by this change in a single bit. If the values are extreme, the fault may be not observed. Extreme values are likely to cause the data statement the saturation while changing by 1 bit due to their small value range. On the contrary, configuring the values to be intermediately effective in preventing data saturation while changing the values by 1 bit caused by the variable changes larger than for extreme values. As often safety in the system performance is degraded due to the fault. In general, performance improvement of IPUs such as cache MA only reduce performance without system hang and data mismatches when the fault is injected. The performance is important to the system, and one should define test scenarios at a system level that should catch the difference when the performance is satisfied. Therefore, the fault can only cause only performance difference can be found at the system level, and the IP itself is considered to be safe. The debug methodology. The most important part of the FC is result analysis to meet the target DC, and in UU cases, the engineer must see the expert judgment to define whether it is safe fault or additional scenarios are required. On software end, the hardware method can be used for finding a fault propagate in the system. Using a software method encountering the expectation is that a monitor of the core CPU may capture the region while the fault propagation is hidden. Also, comparing the waveform faster triage between the code run and check run can be one of the approaches based on the hardware to figure out when the fault propagation is masked. By having these debug methodologies, the engineers can debug point and board scenarios to get the expected DC. The UU analysis. Non-injectable nets can, based on the synthesized information of vector quality, are already featured by the compiler and DB optimized net by applying the vector analysis VQC, and the classification of the fourth generation loan with the injectable net is needed based on the resolution report. The following three methods are used for this FC: fast triage, configuration check, and read transition checks. Fast triage logic. The main concept of the fast triage is to find how the propagation by injection fault cannot be spread out and where the propagation reach out to the alarm net and the observed net. The result of the fast triage can be classified as a safe fault in the expert judgment based on the evidence why the fault effect is not propagated. Since the Veloce supported the utility 2, the compared to waveform, usually the deviation between the golden run and the check run can be found as long as two waveforms are ready. By comparing the port of the hierarchical modules from the 14 injection net of FI and the alarm net can be, and the observed net of the deviation can be found. If the deviation between the golden run and the check run is found in the output of the module 2 in figure 4, while no deviation is found at the input of the module, which has the alarm net, which can be a safety fault because the fault effect is not propagated to the alarm net. Then it can be assumed that there is a logic that bridge blocks effort to a fault propagation in module 2 or the module 1. Like this. The figure 4 is the fast triage concept. So this is one of the cases why the deviation by fault propagation cannot be found. The deviation on out A was not found because the value A and X and Y is golden run and check run were same in the current test scenarios, figure 5, while there was some total values on the value A, X, Y in a golden run, value A and X, Y, 1 was stuck and the check run. However, when a value of the value A is golden run was 1, which is the same as the values in check run, so can be a safety fault because there was no deviation between the golden run and the check run. The figure 5 is simply code for the UU case. The configuration check is deal with the ARM core. If their core has a safety mechanism such as ECC or wrap parity fault is injected in the cell, the configuration needs to be checked whether this safety mechanism is enabled or not. If the ARM is not familiar, this is hard to debug on waveform is a software code. If safety engineers can have both access to the software code and synchronize waveform at the same time, it is helpful to check the configuration environment such as the enable of the ECC, parity, and watchdog. If a safety engineer is familiar with the waveform, the engineer can trace back software by moving waveform time frame back and the forth. If the safety trigger in the familiar with the software, the engineer can break point on software so that the waveform shows the current status of the hardware, which is a Veloce application can support this methodology. Read transient check memory. For this case of injecting the fault on a memory cell, and the fault cannot be propagated towards several receivers unless the system reads the data from the cell to provide whether the fault propagation affected the receivers or not. The address and read address needs to be verified. In the case of figure 6, read transaction can be checked with the values of enable A. If there isn't a transition with the current test scenarios, it can be a safer fault because the injected fault cannot be propagated further. Figure 6 is a snip code for a read transaction. So the chapter 4 is the research and analysis. The FC requires several iterations before the expected DC was achieved. After each iteration, one should analyze the UU cases and general test scenarios and rerun the FC. C is analysis of the research and updated test scenarios for PU, P1, and MEM. NPU architecture data flow and algorithm were analyzed, and above the mentioned method were applied at iteration table 5, namely the list those steps were taken. 1. After checking the bit width processed by the sub-IP, two special data patterns were created. for the former MSB1 and others all 0, and for the latter MSB0 and others all 1. If there was 2 or more input that affected output of the sub-IP, that the special data patterns were supplied to only one input, and the data and other inputs were simplified so the value changed by 1 bit can propagate the end of the IP chain. Creating input data in this way increases the data sensitivity for the fault injected into small special data patterns, making it easier to generate output failures. 3. The NPU IP has an active feature using LUT, and for nonlinear functions and operations using the LUT has a chain structure. After several LUTs are used in one test scenario, then due to the injected fault values of each LUT of the chain can be very variable and result in a considerable data saturation. To prevent this, target LUT was set for each test scenario. All other LUTs were bypassed, so that test scenarios were created in a way that minimized the influence of LUT. 4. The result of MAC is MAC. MAC is a combination of multiple suppliers' errors. If the result is configured to be only positive or only negative, the data saturation is often expected due to the clipping. To avoid this, input was created so that the output data also generated intermediate values. For example, the output of data is assigned values. 0 value was created as sum of the positive value and negative value. This output data can improve the sensitivity by default because it can increase the range of the outputs can be changed by default. To cover the register logic, additional test scenarios was created. Value 0 and value 1 were consecutively written, read, and compare. This method indicates an error due to the default. The test scenario was more efficient in terms of runtime compared to normal test cases for registers where random values were used. After table 4 is a percentage of do for SM3 PU0 block. After updating the test scenarios, a formal analysis was used to check the count of influence of the remaining UU cases. The faults were in which were outside of the COI were marked as safe fault. 2. Then, to increase DC, more expert judgment was applied to the remaining UU cases. The fault of the spec-out feature is a safe fault. If the hardware feature not included in software scenario existed in the IP, then the fault injected in the related module, register, port, and etc. were marked as a safe fault, spec-out. The fault of the debug feature is a safe fault. Debug features such as performance monitors and internal counters for debug do not affect the output of the IP, so that the related fault were marked as safe fault debug. The fault of the clock gating, the disabled feature, is a safe fault. The fault which is disabled the clock gating logic intended for power reduction does not affect the output, so they were marked as a safe fault power. The fault of the invalid range bit is a safe fault. The valid range of the register port may be limited depending on the scenario. The faults of the invalid range do not affect the output, so they were marked as a safe fault configuration. So the fault of the performance feature is a safe fault. Features that only increase or decrease the performance do not affect system hang and output data dispatching, so they were marked as safe fault performance. The analysis of the result and updates for the test scenarios for PU2. PU2 itself consists of several parts. To get a high score, test scenarios should cover all of them, including the computing core, memory, command, schedule, bus, and memory access blocks. At the first iteration of your software test scenarios was used, but it only touches algorithms logic, partially some related registers, and almost none of the other registers like control and other logics. Table 6 is the test scenario from functional verification was applied. It includes all arithmetic logics. So the memory operation were not enough, they were added also. So after full analysis of the UU case, it was found that some registers had specific patterns, it was added also. The result FC. In table 6 is the percentage of due for SM3 as PU block. And the E is the result of the FC. The final DC was calculated as sum of the DU compile optimized the logic, the port in MEM, COI, and safe. Divided the differences of the total a fault is list and compile, optimize the FIN and the FDN, DC, DU, D0, compile, and let logic for no port in MEM 5 in FIN and FDN 6, CO1, 7, and safe 8, fault list 1. The result of the FC for FM3s are shown in the table 7, and the final suit for the FM3 includes the thoroughly optimized test cases, test scenarios with high efficiency and low runtime. Table 7 is the result of the FC for SM3 self-test. The result of the FC for SM1, SM2 CPU part are shown in the table 8. For SM1 software test library, STL and custom test scenarios were used. For SM1 and only, STL was used for proper configuration settings were checked with the code link. As the number of test scenarios provided by the ARM is limited, the additional analysis of remaining UU cases using the debug methodology with the code link mentioned earlier is planned for the future work. Table 8 is the result of the FC for FM1, FM2, and Chapter 5 is summary. The functional safety workflow of NPU IP was the software-based SM is presented. The internal blocks and related SM were selected based on the FIT rate distribution. The FC process, including the fault injection run by emulation, was applied. Debug method for efficient UU analysis was introduced. At each FC iteration, after the detailed analysis of the IP architecture and fault, test scenarios were updated, and a final sum remaining faults were classified as safe. The target DC score of 91.21% necessary to meet the ASIL B matrix was achieved. Further optimization of the test scenario runtime for software safety verification can be included in the future. References like the 1, 2, 3, and so forth. Today I read this paper, the functional safety workload of internal IP with a large automotive IC through analysis and emulation usage for software-based safety mechanism. Thank you for your time. See you next time.